and welcome back. We're up to 3.6 in Chapter 6. After this one, only one more to go, but it'll be 3.8 because we're skipping 3.7. And 3.8 also has some good business applications, so you can look forward to that too. But a little bit of work on asymptotes. Now, the hard part maybe is to spell it or to pronounce it. I'm not sure which is harder, but the asymptotes themselves aren't too bad. Let's get with it. So the first thing I want to do is make sure I've got my pen going. So let's turn that on. Pen, red. Okay, we're ready to go. So, three different things. The last one is, of course, important to us. The first and second ones look as though they're going to be difficult, but actually they're not too bad. So hang in there. Keep a positive attitude. Asymptote, vertical asymptotes, and infinite limits. This is another aid to curve sketching, which is section 3.7, which we're not doing, but there is some application, so we don't want to skip this, and we're not going to hit it too heavily. When you get to the test, you'll notice there won't be too many of those, and that's another thing I'm going to be making pretty soon, is the next test. And of course, you'll get to see a sample of what those questions look like, and play around with them, and see what you can do and what you need to ask questions about. So here's an example of a function. You can see the function up at the top here, circled. You'll notice that in the denominator that points to the fact that you can't just use any old x. Putting a 2 in there is just not allowed. What's interesting though is not only is 2 not allowed, but unusual things happen whether you're coming from the left or from the right to 2 for an x value. This behavior is described by saying the line x equals 2 is a vertical asymptote. Take a quick look back here again. What it's approaching is x equals 2, which is a vertical line. That makes that line that it's getting close to an asymptote. That's what asymptotes are, whether it's vertical or horizontal. Some line that your graph is getting close to. In this case, it's getting close to that line, and depending on which side you come from, it's either going to positive infinity or negative infinity. Quick look back there. So how about this one? The infinite limits for the function can be written as, so we can write it like this. Notice that this little minus sign does not mean minus 2, that would be out here for a minus 2. It means, sort of in essence, shave just a little bit off of the 2, so it's 1.99 whatever. It's getting close, but from the left-hand side. Now what you might want to do is grab your calculator and see what happens when you get numbers that are close to 2 and you put them in here, but not quite 2, just a little bit less than 2. And then get closer and closer and closer. That's where it's great having a calculator. You can play around with this and do 6 or 10 of these examples and see what exactly is happening. If you're familiar with a table function in your calculator, that would be another possibility too. I don't usually do that, but it's a possibility. Remember, that's as x approaches 2 from the left. And from the right, you get a different limit. So here's the definition of that vertical asymptote. This is your asymptote. It's what your graph f of x is getting close to when the x values are getting close to this number right here, x equals c. Remember, the c represents a constant. It could be a 5, 92, 14, 30 seconds, whatever. So this is a little bit of a general thought on the whole thing. Usually you have vertical asymptotes when your function is a rational function. That means there's a function on the top and a function on the bottom of your rational expression, your numerator and denominator. Now you have to make sure that if q of c equals 0 and you don't have 0 up above, then the graph of f can't actually get there and has a vertical asymptote at x equals c. Now that means we're not actually putting c into the q function, but when you get close to that value of c, unusual things happen. In particular, that means it's as you get close to c, you'll see something like this or something like that happening. We've got, I think, 4 examples here. Here's the first one. Here's our function. Here's the graph down here. Coming from the left. That minus sign means we're coming from the left. That's what's happening. As you come from the left, your graph is getting closer and closer to that x equals 1. From the other side, this is from the right side. This is 1 plus just a hair more. What's happening? Well, as it gets close to 1, it goes to positive, and the y values go to positive infinity. Remember, those limits are talking about what does the y value do when you get up close and personal to the 1. Example number 2, just a little bit different. Again, this is approaching from the left, and this is what the graph is doing in this case. As you get closer to that 1, the y values approach infinity. On the other side, approaching from the right, as you're approaching 1 on this side, your y values are getting close to negative infinity. Just like that. It's not hard, and if you can't do these in your head, and sometimes I can, sometimes I can't, you can always experiment with your calculator. If this were 60, 70 years ago and there were no graphing calculators, it would take a bit of time to play around like that. But your calculators make it great. You can put this in your calculator and just keep changing the x's and see what happens as you get closer and closer to 1. Third example, a little bit different from the other one. Notice we've got negative 1 here, but we've got x minus 1 squared in the denominator instead of just x minus 1. Now that means this will always be positive, and since this is a negative number, this whole thing will always be negative. So notice the entire graph is below the x-axis. Again, this one is approaching 1 from the left. That means we're down here, and as we get close to 1, we're getting close to, our y values are getting closer to negative infinity, or heading that way. It's not actually getting there. From the other side, getting close to 1, the y values are getting close to negative infinity again, because a negative over a positive, this can never be 0, gives you a negative number, and as the closer it gets to that 1, and then squared, it's going to give you bigger and bigger negative numbers. Last of all, this one's like the first one, except that you got 1 over x minus 1 squared this time. Here we're approaching 1 from the left. We've got negative 1. And over here on the graph, you can see as we get closer to 1, the y values get bigger and bigger and bigger. On the other side, approaching from the right, we approach positive infinity. Nothing really terrible there. Here's one for us to play with. Find all vertical asymptotes of the graph of f(x). Where are any, if there are any, where there are vertical lines that our graph is getting close to? First, if you're able to, factor the numerator and denominator. So here's a new trick. If you can factor this, and if you can factor that, it might make a big difference. In this case, it does. Look at what we've got. Both of those have a factor of x minus 1. We're going to be able to cancel those out. Now, it only cancels out in a certain way. With those gone, replaced by a 1, that means most of the time your graph is going to look like this. But because this x minus 2 was there to begin with, you still won't be able to use an x of a 2, because even though you can reduce it, this still affects how your graph is working. So there you divide out the common factors. That's what it looks like most of the time, but you do have to stay away from that too. So what is going to give you the vertical asymptotes? Well, it's what makes the denominator a 0. So set that equal to 0. There is your vertical asymptote. Remember also that all vertical asymptotes will look like x equals, and then it depends on what your function actually has. X equals will be for all vertical asymptotes. Next, the denominator isn't 0, but what happens? When it gets close to negative 2 from the left, it's going to toward negative infinity. From the other side, except for right here, can't use that point. On this side of this, as it approaches negative 2, we're approaching positive infinity. It's a good excuse for playing around with mathematics, really. And the calculator is invaluable for this experimentation. Notice that also that even though this was in the denominator to begin with, because we were able to cancel it out, it's not a vertical asymptote, but it does contribute to this whole because we can't use that number. Horizontal asymptotes. Now looking ahead, keep in mind there's going to be 3 rules that help you find horizontal asymptotes. 3 rules. You want to write these down, If you want a copy of these slides, I'd be glad to send you. You've got something very similar on Moodle, but this is a little bit different. I've spent quite a bit of time to make it ready for these presentations. So here we go. A limit at infinity. So what does that mean? Well, it means, if you look at your limit down here, instead of having x approach a 5 or a 6 or a negative 2, it's approaching infinity or negative infinity. So that's a little bit different. The x values are going to get very big or very, very big negatively. And that's going to give you horizontal asymptotes. So here we go. Here's an example of two ways you can get horizontal asymptotes. One way is this first one has a horizontal asymptote down below the x-axis, where it's approaching y equals whatever this number is here. And to the right, it's approaching some number up here. Now remember, the vertical asymptotes were x equals. The horizontal asymptotes, these lines are going to be y equals something. Vertical asymptotes, x equals. Horizontal asymptotes, y equals. Notice that this one does this sort of thing. You can approach different ones on different sides. This one takes its time. If you're thinking of it from left to right, it takes its time actually getting close to the asymptote. But eventually it sort of, you might say it sort of settles down and approaches whatever this line is. Y equals something. Maybe a 2, maybe a 1, whatever. Also note that it's possible for the function to cross its horizontal asymptote. So this odd one over here actually crosses where it's going to come close to, goes away from it, and then starts coming back and getting close to that horizontal asymptote. Now here's a property to keep in mind. Translated, what this is actually saying is that in this case where x approaches infinity, that means this number, as long as r is positive, this number is going to get bigger and bigger and bigger and bigger, just out of bounds. That means 1 over that is going to be smaller and smaller and smaller and smaller until it disappears. On this side, what it's saying is x is approaching negative infinity. So if you put negative numbers in here, you're eventually going to get a lot of negative values. The bigger this x gets, the smaller this is going to get, very similar to over here, and both of them are going to approach 0. Translated, that means we're going to get close to y equals 0. Well, here we've got something to play with. Imagine that. So, one thing, remember, you can do with this, I know it's been a long time since you saw the limits. That was back in chapter 1, either the last or the next to the last section in chapter 1. You might take a look back there, just at the properties if nothing else, just to remind yourself. One of the things you can do, just like with derivatives, if you want the limit of this difference, or if it's a plus, you can always split it up into the limit of 5 minus the limit of this fraction. It makes things a whole lot easier. So we split them up like this. There's our property on the right in red, just as a reminder. So you work those separately. Now over here, in this part, remember x is approaching infinity, it's getting bigger and bigger and bigger, but all we have here is 5. X does not affect what 5 is. So this stays 5, period. Don't make it complicated. And we need to find out what's inside here. Now if you looked at the previous screen, you know that if x is approaching infinity, then this is getting extremely big positively, especially since it's squared. But it's only got 1 in the numerator, so the bigger the x gets, the smaller the 1 over x squared gets, until it basically disappears. You get 0 there, and even if you have it times 2, you still get 0. So there is your limit of the whole thing. There's a picture of what's going on. Notice here's your equation, here's your function, and this is what the graph looks like. Notice from here that you've got x in the denominator, so x can't be 0, so you've got a vertical asymptote at x equals 0, and you've got a horizontal asymptote, which we just found. It won't go as high as 5. It'll get close, but it won't get there, regardless whether you go to positive out here or negative infinity for your x values. So here are the notes you want to know. 3 notes. I'll put some stars in here for you to focus on. First of all, it says, let me switch to the pen. If the degree of the numerator is less than the degree of the denominator. Okay, what does that mean? This means, we'll just put a number up there. Doesn't matter what it is. If you've got something here that has a bigger degree here than it does up there. So let's suppose, let me make this. Suppose we've got x to the 17th here and x to the 22nd there. The deal with number 1 is, if the degree in the denominator is bigger, then you're going to have y equals 0 as your horizontal asymptote. Very easy. All you have to do is look at the degree of the function. What's the degree of the numerator? And what's the degree of the denominator? If this one if the one on top has a smaller degree, then your horizontal asymptote is y equals 0. Very simple. That's because if the leading term down below has a higher degree, then if you look at just these two, even if there's a 7 here and a 5 there, that's irrelevant. It's the degrees that make the difference. If the degree down here is bigger, then when you actually work this out, this one down here has a degree 5 higher than what's on the top. So if you make x very, very big or very, very small, you're going to have whatever number on the top here and a very big number almost infinite on the bottom, which means the whole thing is going to get close to 0, and that means y equals 0 is your horizontal asymptote. So last comment here, smaller on top, larger on the bottom. We're just talking about the degrees of the polynomials. If you see that immediately, go for this. You've got a horizontal asymptote at y equals 0. End of that story. You might have other things, but you've got y equals 0. If you don't have that, look at degrees again. Let's move ahead here. If the degree of the numerator is equal, so, where am I? There we go. So we've got a function, and we've got something x to the n, let's say, over something x to the same exponent. And you've got some more terms down here. What's important is these degrees are the same. The polynomials are the same degree. And if those are of the same degree, then what you'll do is you'll look at these two numbers, the leading coefficients. In this case, the a and the b. So you'd have a, say, x to the 5th over b, x to the same one. And you might have some other terms, but the leading one is the one that draws you to an asymptote. If this is the case where the degrees of the polynomials are the same, then these two will give you a horizontal asymptote. And it'll be very simple. Y equals a over b, period. So look for the degree on the bottom being bigger, that gives you y equals 0. If the degrees are the same, then all you have to do is look at the coefficients of the leading terms in the numerator and denominator. And y equals a over b will be a horizontal asymptote of the graph of that function. Third, if neither of those is the case, if the degree on the top is larger, then there's no horizontal asymptote at all. So if for some reason you were hoping for a horizontal asymptote, I'm sorry, there won't be any. There might be a vertical one, you can check that out with the denominator, but no horizontal one. Alright, so let's see what we've got. See if we can actually do this. So, first one. Remember, we're talking about horizontal asymptotes. So we've got 3 rules. All we need to do is look at what's the degree of the polynomial. The degree of the one on the top is just 1 because we've got x to the first, and that's the leading term. On the bottom, the leading term has a 2. So the degree on the bottom is a 2. This one is larger, and if the denominator is larger degree, then our horizontal asymptote exists, and it's y equals 0. You don't even have to worry about what the number is. It's y equals 0. End of story. See if you got another one. For part B, look at the exponents of the leading terms. They're the same. But we don't care about this part right away. That means since degree on the top equals the degree on the bottom, you get a horizontal asymptote. Now you go back and see, okay, these had the same degree. Now we'll look at the coefficients. And the coefficients are going to give us our horizontal asymptote. Just strip away the rest of the top and the rest of the bottom, and there is your horizontal asymptote. Part 3. Notice that in this one, the degree on the top is bigger, so no horizontal asymptotes. If you're looking for one, I'm sorry. There's the first one. That's the one that had y equals 0 as the asymptote. Notice it slips down underneath, but then it is getting closer to y equals 0. Y equals 0 is the horizontal asymptote. For the second one, the degrees were the same, so our horizontal asymptote was y equals negative 2 over 3. There's your horizontal asymptote, and you can see a picture there. And the third one, the degree on the top was larger, so there's no horizontal asymptote. What you might notice is you sort of have an asymptote, but the point is there's no vertical asymptote, no horizontal asymptote. Just for your information, now this is sort of strange. This is one piece that wasn't showing on this list. In pre-calculus and in college algebra, you actually had one other piece for asymptotes. If the degree on the top and the degree on the bottom are differing by 1, larger by 1, you do have an asymptote. Excuse my drawing, but it is getting close to this line. It's a slant asymptote. It's not vertical, not horizontal. So this is called a slant asymptote. And that involves doing some division, and we're not going to get into that, but there is another one, just in case someone should bring that up. If you went to a tutor and they said, well, what about the slant asymptotes? Don't you worry about that? Or aren't you concerned about that? Well, we're not going to bother with that. We have enough to do without slant asymptotes, right? So, application, of course. This is a good example for throwing in average functions again. Remember, C represents the average cost function, but it's not the average, total cost function. This one is talking about the average cost. That means C bar. And remember that's C over X. So whatever the C is, you'd have to put that in here. And if possible, simplify to get your average cost function. So we've got 4 different things we want to look at here before we wrap this up. We want to find the average cost per unit when 1,000 units are produced. So perhaps where you're producing pens or whatever you want to make up. Then we're going to jump from 1,000 to 10,000 to 100,000 and see what that does with the average cost per unit. In other words, does it help your cost per unit if you make more of them? Now up here at the top it says they invest $5,000 in a new product. that probably means, well, it might mean that they've bought some kind of machine. If your business is selling pens, for example, ballpoint pens, perhaps you buy a machine for $5,000. Well, that $5,000 is part of your total cost, and it's going to affect how much you have to pay or sell the product for. The product's going to cost 50 cents per unit, okay, but you still have to make up the $5,000 to be able to get a profit. So here's how it goes. Here's our total cost function, because 5,000 is first. In fact, one alternate way of writing it is, even if you're not making any pens today, you still have to pay that $5,000, or you have it paid for the machine or whatever it costs. Plus, for every one of those pens, you're going to have to pay 50 cents to make that pen. So if you make 7 pens, 7 times 50 cents, plus the $5,000 that you have to pay because of the machine, or whatever the fixed costs are. So here's our average cost function. I mentioned that earlier. Remember, this is the average cost function. That's the total cost function. The total cost divided by the demand, or the number of units, gives you the average cost function. So what we've got is the average cost function is 0.5 plus 5,000 over x. Remember, we got that from taking this and dividing the whole thing by x. So 0.5x over x, the x is cancelled, you get the 0.5, 5,000 over x is 5,000 over x. So there's our average cost function for us. Now, we get to actually start to work the problem. If you're producing 1,000 units, how much does it cost? All you have to do is put 1,000 in where the x is. It's going to cost you $5.50 for each of those pens, or whatever you're making, to actually make them. That's the average cost. So 1,000 units, each one on average costs you $5.50. For 10,000, just put the 10,000 in where the x is. It's going to cost you $1 then, instead of $5.50. Oh, that's interesting. You go from a unit cost of $5.50 to $1. That's quite a reduction in going from 1,000 to 10,000 of those pens, or whatever you're making. How about you up it to 100,000 units? Just put the 100,000 in where the x is, and your average cost is down to 55 cents per pen. What if we even ran it up further and made more pens, or whatever we're making? Well, there's your limit again. That's why you want to remember, that's why we wanted to use the limits back there. Not only does it define the derivative, but it's handy up here too. So you take the limit as x is approaching infinity. In other words, you're making more and more of those items, whatever they are. So what do you get? Well, split them. Put the limit of 0.5 plus the limit of 5,000 over x. The limit of 0.5 is 0.5. The limit of the 5,000 over x, and this doesn't change regardless of what the x does. This does. If this gets sufficiently big, then even dividing in the 5,000 will make this almost 0. And if you're talking about money, that means maybe 1/10,000th of a cent. In other words, almost nothing. Here, as a final, here's a picture of what it looks like. When you've got a small number of units, like we have here, small number of units, the price per item is pretty high. You make more of them, the price per unit isn't quite as big. Make more of them, the price per unit is smaller. But it approaches an asymptote. You're not going to make those for less than 50 cents a piece. Get close, but that's the limit. And that's it for this section. I hope you enjoyed part of it, and bring your questions to class. Do some of the practice. Keep in mind that we do have a test coming up sometime soon, and most of that test will be applications. We won't be focusing directly on asymptotes. That'll be just a tool. But I'll be sending you out a bunch of samples of problems, things that you ought to know before you get out of business calculus and you ought to take with you. Well, adios.